There is an urgent necessity for reduction of dangerous environmental impact in the energy production, and for maintaining a secured and low-cost energy resource supply. Current organic photovoltaic cell designs made a significant step towards low-cost solar cell technology. However, in order to be competitive with silicium and CIGS technologies, organic photovoltaics still have to demonstrate power conversion efficiencies above 10% and a long-term stability in the application, beside aesthetic flexibility and low cost. Real breakthroughs will come from dedicated material development and innovative device concept. However, in order to be really competitive with existing technologies worldwide and on European level, and see a large market development, further improvement on efficiency, stability and cost are needed. The highest certified power conversion efficiency for organic solar cells, OPV and DSC, is today over 11%, but the efficiency limits and stability problems are the current bottlenecks. The MOLESOL project comes with a novel concept of hybrid device, combining the advantages of both concept OPV and DSC, an all-carbon platform for highly efficient molecular wire-coupled dye-sensitized solar cells. The proposed technology goes beyond the current state-of-the-art dye-sensitized solar cells technology by working with a new principle, combining the assembled dye monolayers linked by organic molecular wires with transparent inorganic carbon-based thin films, diamond or graphene, deposited on optically transparent substrate and effectively collecting the photo-generated charge. The scientific and technical methodology of the MOLESOL project is based on the organization of activities into 5 complementary work packages. Each work package is composed of several tasks. The ensemble forms a coherent work plan of interconnected activities.
Yeah, as you know, IMOMEC is part of IMEC, and IMEC is the largest European independent research institute on microelectronics. We develop materials that can be used in devices.
Diamond materials are a range of materials, not just the single crystal gems that you can buy in the jewelry store. We can now grow diamond materials with grain sizes ranging from the nanometer scale all the way up to the centimeter scale. And depending on the technological application, we can engineer the material to that application, either through changing its color, its doping, its electronic properties, or even its surface properties.
The main reason why we use diamond in the MOLESOL project is that we can make a very thin layer of transparent diamond on any type of substrate. But most important is we can make it electrically conductive, and being diamond, it is a carbon surface which can be then functionalized, forming very stable bonds with all kinds of dyes.
We will use cyclic voltammetry scan techniques to functionalize the diamond surface with aerial boronic esters, so that the functionalized layer can then be used as a platform for subsequent Suzuki cross-coupling reaction with the molecular dyes. The cyclic voltammetry functionalization will be performed using a potential stat controlled by a GPES software. I will now pour the solution inside the reaction flux. The diamond electrode to be functionalized itself will be acting as a working electrode. We can now start to functionalize the diamond.
And we think of diamonds being grown in the mantle of the earth, or more recently in high pressure, high temperature presses. But in the last few decades, we've also learned how to grow diamond at less than 1 atmosphere pressure in partial vacuums. And that raises a lot of interesting chemistry about how we can grow these diamond materials. And so what we're interested in is really what is the flux of the atoms and chemical species in the gas phase to the diamond surface that enables us to grow diamond as opposed to other forms of carbon, such as the more stable graphite. So one of the areas that we've been researching heavily for the last several decades has been the composition of these, what we call plasmas, that can generate the radicals and the atomic species necessary for growing diamond. This reactor will actually work at much different pressures than most what I would call the current technology that's out there. It works at much lower pressures, and so it opens up new chemical channels for us to understand the growth of diamond.
A plasma to grow diamond, by adding a boron-containing compound into the gas phase, we can make the diamond electrically conductive. The advantage of having these charges in there is that by then fixating a dye on the surface, which captures the solar light, is that these charges that are created by capturing the light can then be transferred into the diamond substrate and onto the continuous layers which are forming the complete device. Because the conductivity levels of the diamond are maybe not so good as competing materials, there are a few tricks that we can apply here. We can make use of a metal grid underneath the diamond substrate. We can have different types of fill factors of these metal grids. And a big advantage is, with other traditional substrate, is that the dyes which are on top of those substrate are just spin-coated or just fizzy-sorbed, while on the diamond surface you can make a chemical bond enabling a better charge transfer from the dye into the diamond substrate.
Graphene oxide films were treated in CH4 plasma condition. The treatment time can be as short as 10 seconds, yet resulting in samples with a sheet resistance of 5.2 kilo-ohm square and about 80% transmittance. Samples with a sheet resistance of about 450 ohm square with transmittance over 95% were obtained. The sheet resistance were further decreased by the combination of gold grit and graphene, resulting in a sheet resistance of about 30 ohm square and around 80% transmittance.
For the diamond functionalization, we use a stepwise approach, starting from the boron-doped diamond sample, which we functionalize in an electrochemical way. So we decorate it with functionalized phenyl moieties. For example, we can use boronic esters. Then in the next step, we want to couple a dye to this functionalized diamond, and for that we need a complementary function to the boronic ester, which could be a bromine group on an aryl. As an example, I will draw a cyclopentadiethiaphene, which looks like this, which is decorated with alkyl chains here. These two are coupled together. We have a larger structure, and in the end, at the other side, we still have a site available to couple alternative dye molecules to construct the whole diamond functionalized sample.
Many donor P acceptors were developed by IMEC and EPFL towards P sensitizer to be coupled on functionalized boron-doped diamond substrates, requesting a high know-how chemical design and synthesis. Most of them are based on cyclopentadithiophene donor unit. Also, N-type sensitizers were developed by EPFL based on squaren to be coupled to graphene electrodes. Numerous advanced synthesis and analytical tools are used. For example, microflow synthesis reactors or FTER probes. But also more classical UVVs or NMR for characterization of the new materials.
The molecular dyes can be now coupled to the aryl boronic ester functionalized diamond through Suzuki cross-coupling reactions. In this transferring chamber, the flux will be vacuumed and purged with nitrogen gas. Inside the oil bath, after setting the correct temperature, and I will start the reaction for 18 hours.
Developed in collaboration between IMEC and NUS in Singapore, it was found out that graphene coupled to diamond via a molecular wire gave more efficient charge collection to enable generation of higher photocurrent. The information related to interface properties between dye and substrate can be extracted from XPS and UPS. Also, other methods of characterization were used. Raman spectroscopy, which is a very suitable tool for physical characterization of boron-doped diamond films, non-diamond carbon impurity phases, and boron doping levels. Electrochemical impedance spectroscopy helps to define what is happening at the interface, surface optimization and quality control. The surface morphology was evaluated by tapping mode atomic force microscopy. Finally, molecular wire coupled dye-sensitized solar cells were tested by photoelectrochemistry. Graphene inks with low sheet resistance able to replace the platinum catalyst typically employed on the counter electrode of a traditional dye-sensitized solar cells were formulated.
We will need a molecular dyes functionalized diamond electrode as the photocathode, a platinized coated FTO counter electrode, or graphene-coated FTO electrodes, and a polymer. And these electrodes are sandwiched together by applying heat using this hot press. After applying heat, the polymer will seal the two electrodes together, and the product will look like this. And then we will inject the electrolyte, redox electrolyte, through the hole inside the device. And then we will seal again the hole with a polymer. And the final device will look like this.
In industry, more sophisticated equipments for large-scale production is used. Various types of modules and demonstrators are fabricated. Mini modules, non-conventional shape, or panel on flexible substrates. 35 researchers from 8 organizations were involved. Synthetic chemists, physicists, engineers from academia, research centers, SME and industry, from 7 different European countries: Belgium, Czech Republic, Ireland, Italy, Germany, Sweden, Switzerland, and from 1/3 country, Singapore, the best expert in complementary field on European scale. This project, co-funded by the European Commission under the 7th Framework Programme, is developing materials, novel device concept, and proof of principle for tomorrow applications. Are we ready for sustainable energy production?